Uh, Good afternoon. First, I'd like to thank the organizer for this very kind invitation and opportunity to speak here. And I'll excuse my right to change a little bit off topic of the conference. So I speak about classical mechanics. Let me first give you the motivation why I decided to speak about classical mechanics in a quantum mechanics conference. Basically, the motivation comes from some non-equilibrium or far from equilibrium solutions which we came across in quantum systems, strongly interacting quantum systems which are coupled to some thermal baths. And we would like to understand if these solutions, by the way, these solutions gave birth to these quasi-local charges, which many people are now excited about, and they are sort of related also to the concept of thermalization and quench dynamics. But I'd like to come back basically to the motivation for that, and motivation came from looking at this strongly driven interacting theories in one dimension, which are driven by coupling them to the boundaries at the sides of the chain. So what I'm doing now is basically trying to ask whether I can dequantize such models, and whether I can come across a model which is even simpler than that. So we all love spin chains, but the question is, can we have even simpler models which have all the mechanisms that we have, that's exaggerating, but which have the mechanisms which we like to understand in spin chains. So basically, that's the idea. Find an abstract model of non-equilibrium transport in conservative reversible interacting systems. Yeah? We know that basically, we are interested in Hamiltonian dynamics, which is basically conservative and reversible. So can we do it in classical mechanics as well? So, and I will try to argue that there is a simple such, well, this is my argument, but I'm willing to discuss. I'm going to present a reversible cellular automaton with stochastic boundaries, which is exactly solvable. So I'm discussing now exact solution for such a model. Now, this model is, okay, you may say it's very non-physical, that's true, but anyway, it's a paradigm or metaphor of what we are all interested in. So, and then I would like to investigate the mechanism of integrability of non-equilibrium steady states of such model. Okay, this work has been just put in the archive or submitted a few weeks ago, so it's a really fresh thing, and basically it's the first time I'm talking about this in the international conference. Okay, so basically the model is kind of well known. It's been discussed in the 90s in this very nice paper by Bobenko et al. In Communications in Mathematical Physics in '93. They classified more or less integrable cellular automata over the field of Z2. That is the simplest cellular automata you think of, but they have to be reversible. So basically we have two layers in time, or even better, you can write them on the diamond lattice. So time always, in my talk, time always runs vertically, up, top, down. Yeah? So that's the cellular automaton which I'm going to discuss. That's kind of trivial, almost trivial, but the interesting parts come from stochastic boundaries, yeah, which I'm going to present later. But let me just, to set the stage, let me describe this model. This is the so-called code 54 reversible cellular automaton of Bobenko et al. So basically you have 8 possible neighborhoods of 3 cells. So there are the 3 cells which are the west, east, and north cells, and the mapping is the state of the southern cell, right? So this is 0, 1, 1, 0, 1, 1, 0, 0. That's 54. Yeah. So that's basically the rule. It turns out this rule gives rise to some sort of integrable dynamics. It has been not clear. If you read this paper by Bobenko et al., basically they don't present Lux pair, and they don't present zero curvature condition for that particular cellular automaton. They just argue it's like a soliton dynamics, but then they go on and discuss some sort of Hirota equation over finite fields where they really present Lux formalism. So this model is kind of strange. It doesn't really fit to the picture, but it looks to have very nice dynamics. So that's why I argue this is the simplest strongly interacting model, because the solution, this is a typical solution which looks like this. This is 1 + 1 dimension, this is space, this is time. So this is some initial condition, which is the state of the zigzag lattice, and then this is black is occupied, white is empty. Yeah? So you see this is like a scattering of solitons, and the only effect of scattering is some time lag, yeah? Some phase shift. But anyway, this gives rise to some, yeah.
All these moves, they occur with the same probability.
No, there's no probability. Sorry for, thanks for asking. It's purely deterministic. That's the idea. Otherwise, you would say, okay, I mean, we have these exclusion processes which are very...
And it's also synchronous, the whole automaton.
Pardon me?
It's also synchronous, it's all at the same time.
Right, it's synchronous, deterministic. Right. It's totally boring if you want that. I mean, the automaton itself.
But what is the rule of updating the automaton?
The rule is this one. I mean, that's the local rule.
What is
The time goes up, down. Yeah. So that's all that you need to know about the rule. It's the code 54. It's reversible. So you can basically, there is this function which I will use, please remember this function. This is the mapping, yeah? This is the Hamiltonian, this is the Newton's law for the rule. Yeah? So it's the value of the south cell is west plus east plus north plus west times east. This is the interaction. It's a strongly interacting model. If there was no such term, this would be like a wave equation. It will only have, you know, left movers and right movers going through each other. Now, since you have this guy, there is a time shift. You go down. Yeah. Okay. So I think it's arguably the simplest strongly interacting model, yeah, which is non-quantum. It's deterministic. Now, okay. So I'm sorry. I think the colors are different than on my screen. So here there should be light gray. But okay. Sorry for that. But I think the other pictures will be better than that. And here I decided to use light gray, but I don't see it here. Anyway, this is like. Now this is now the idea how to describe these dynamics. I mean, you will say, okay, I mean, my dynamics is a permutation, so I don't need to complicate. But I have to complicate because I will introduce stochastic boundaries. And as soon as I introduce stochastic boundaries, then I have a stochastic Markov chain, right? I mean, I have a Markov chain then. So then I will discuss this. But let me just go slowly. So the idea now is, okay, I consider a probability state vector, which I define as P underline, and by underline I designate a tuple of real numbers. In my case, everything is real, no complex numbers, everything is real and positive, only probabilities. So this is a set of probabilities, P0, P1 to P2 to the n minus 1. So little n is the number of cells, S1, S2, S3, S4, S5, and so on. So it's a zigzag lattice. Imagine there was you'll see later, but imagine that there was boxes here. And so, so basically there is a 2 to the n combinations of probabilities. And basically my dynamics acts as a permutation matrix. This U is a huge permutation matrix which maps a vector of probabilities to another vector of probabilities. It's totally, I mean, redundant now. I mean, you didn't have to do this way, but once I'm introducing the boundaries, you'll see that this is the description you have to do. Okay, so this is now basically a sketch how I now construct the whole Markov chain. So now you can ask, I mean, what do you want to do? I mean, of course, in the bulk. So this is now I mean, there should be some light colors here, but I don't see them. Obviously, these light colors in Mathematica don't code correctly to these beamers. But anyway, I'll use strong colors later. So sorry for that. So so this is the state. I mean, this is basically just a cartoon picture how I construct the many-body Markov chain, right? Which corresponds to these dynamics. So we start, basically what I also assume is, assume for simplicity that the number of cells is always even. So there is this zigzag which starts with zig and ends with zag, yeah? So, and then this is the coding, the coding of the cells, 1, 2, 3, and so forth to end, yeah? So basically what we do now is to define such a protocol that we start with a stochastic Markov chain, with a local stochastic Markov chain for the last cell, with some probabilities gamma and delta. These gamma and delta are probabilities. There is a two-state Markov chain which is completely specified by two probabilities, right? Just probability to change the cell or to keep the cell. Yeah. And then there is deterministic map. Deterministic map is just a product of permutations. This P is just a three-body permutation, which is encoding the rule chi, which is the 54 rule. Yeah. And then, okay, this is the so-called U even. Yeah. And then you repeat the same protocol for just changing even and odd, which means that now you start with the local Markov chain, which is E alpha beta, with two other probabilities, and then you keep on with deterministic tensor product of probabilities of permutations. Yeah. So basically, if you want a formula, this is the formula how it goes. So you encode U as U odd times U even. U even is P1, 2, 3, P3, 4, 5, and so on. So these are permutations. These are basically permutations which change the state of cell 2 depending on probabilities on states of cell 1, 2, 3. So it's a kind of conditional permutation, basically, which only can change state of the middle cell and depends on the states of the other two cells. So that's why these guys commute. I mean, P1, 2, 3 commutes with P3, 4, so it doesn't matter which way you write them. Yeah? But then there is this P right, which depends on the values of two last cells, which we will encode in terms of this local Markov times some permutation. Okay? And then there's U, which does the same for the other the other order of even and odd. And then there is the last, first or the last, it doesn't really matter. I mean, basically I decided to
PL and PR are Markov matrices?
Pardon me?
PL and PR are Markov matrices?
PR and PR are Markov matrices. Actually, they all are Markov matrices. Even the permutation is a Markov matrix, but it's a trivial Markov matrix. Yeah? But these are non-trivial Markov matrices, which means they have more than one element in each column.
Just a minute, you said that PR and P left, they only act on the boundaries.
Oh yeah, okay. Now this, yeah, okay. I mean, I was, yeah. If I'm really sorry. Yeah, please look at this picture in the archive version of the paper. Then you will see that there is another gray cell beyond that.
Okay. Which is that you need it as a
which is so you have to also couple it to the stochastic environment, which is Bernoulli process. So first, you imagine that environment is a Bernoulli process, B1 half, 1 half. So it's 0 or 1 with equal probabilities. And then there is this local Markov chain, which is conditional on the last cell. And then you apply the permutation on 3 cells, the one before last, the last, and the bound, and the environment. Okay. And in that way, you get a consistent. Yeah, you should take environment in addition, and that in this way you get a consistent Markov chain, which, by the way, is completely integrable. And this is what I'm.
Stochasticity is going to propagate in.
Exactly. That's what I'm interested in. How the stochasticity propagates into deterministic ballistic dynamics and how it produces interesting steady states. Yeah. So I will now put some shift of chemical potentials of this. Parameterized by these parameters gamma, delta, and alpha, beta, and then you will see how it goes. Yeah. Okay, so let me just finish the exact description of the Markov chain. So this is this, if you want, 54 rule, now in terms of 8 by 8 matrix. And then these are this E alpha beta, which is simply this simplest local two-state quantum chain, Markov chain, and then composed with this environmental Bernoulli process, this amounts to such a 2-body Markov chain for the 2 last cells. Yeah? So this is basically completely specifying now the dynamics. Yeah? So is there some more questions on this? I mean, this is, I guess, is important. Otherwise, it's okay. It's technical. I mean, now you will see pictures, but still, I think it's important to understand how we construct the thing. I mean, it's kind of really. I mean, okay. Basically, it's not so easy. I mean, you can try other protocols in the boundaries, and what you see is that you don't get integrable steady states. So the idea is now just play with boundaries until you get integrable steady states. So what you do is basically compute steady states numerically. That's how we arrived to this solution. You compute numerically, just solving. You know, you construct this 2 to the n by 2 to the n matrix. You compute the fixed point. You look at this Schmidt number. You bipartite it. You look at the Schmidt number, and you want Schmidt number to be small, because we want it to be describable as a kind of an MPS. So now we'll go into the business of tensor networks and MPS for this data. Okay, so but to warm up, let me just show how this looks. I mean, this is just a Monte Carlo dynamics, where you have these stochastic boundaries. Now this is for the case where I would interpret the right boundary to be hot and the left boundary to be warm, meaning that here I prefer to have higher density of solitons and here smaller density of solitons. And you see you have some sort of net soliton current from the right to the left. But that's sort of a Fourier law or Ohm's law for these dynamics. Yeah? And we would like now to understand everything in terms of these parameters, alpha, beta, gamma, delta. Yeah. Okay, so now let's first, okay, now we have defined this Markov chain. Now let's first ask very elementary questions about it. So let's just look at the textbook of Markov chains and ask whether this Markov chain is ergodic and mixing, or whether it's what people would call in this jargon, whether this Markov matrix is irreducible and a priori. When it is irreducible and a priori, then immediately you have unique steady state. So that is, you have a single vector with eigenvalue 1, and then you give, on top of that, you have all other eigenvalues inside unit circle. So you have relaxation to this steady state from any initial state you want. Okay, so there is a first sort of a theorem, if you want, even though it's a very simple thing. Basically, I can prove it with a cartoon. And I'd like to call this proof as a kind, I mean, this is like a provocation. I mean, I don't want to insist on this, but I like to call this mechanism holographic ergodicity, because it's exactly what it is. I mean, you make stochastic boundaries, so you can only touch the boundaries, you cannot touch the bulk. And what the theorems tell you, basically I have to now remind you what theorems tell you. There is this Perron-Frobenius theorem, which tells you that this matrix is aperiodic if for any pair of states, or I will better call it configurations. So this underline S is a configuration. So it's a label of a probability state vector. So it's all possible configurations of these 2 to the n cells, or n cells, all possible 2 to the n configurations. So what the theorem tells you is that if you can show that there is some time t such that it's the other way around. So for any pair of S and S prime, there has to be such t that this u to the t is positive between S and S prime. So there is a process. There is a Markov. There's a path in the Markov graph which connects any pair of configurations. Yeah. And it's very easy to see how one can show that. Basically, this is why basically one can just one should demonstrate the following. This is basically a cartoon proof of this theorem. Now what I do is now I plot arbitrary configuration in the beginning and arbitrary configuration at the end. So now I have to arrive at the protocol. I have now to show that there is a protocol which uses a deterministic protocol, which uses 54 RCA rule, going from blue to red, and there are appropriate boundary conditions. And these boundary conditions now should not be stochastic, but there should be a definite choice. When I go through a Markov graph, I should decide which path I do at each node, which means I pick one process of the boundary, right? And this I do in a way that I absorb solitons first, and then I emit solitons second. But how should I emit solitons to arrive at the given state? I just do the time reversal, right? I use the fact that the dynamics is time reversible. So I have unique boundary conditions which drive me from any blue to any red. And then infinitely many steps.
So basically you build like this and like this, but if they open, well.
No. I mean, the point is there should be sufficiently large t. T depends on n.
Okay, then
I can estimate t is less than n squared, so this is a gap. So I can also give you statements about the Ljubljana gap, about the gap and so on. Okay, that's very elementary. I mean, but it's nice kind of because there is pictorial proof. Yeah. Okay. So, okay, but now let's go to the, let's say, theorem 2, which is the more interesting one. How does the steady state look like? So what is the steady state here? I mean, since this is a second order, I mean, reversible dynamics or Hamiltonian dynamics is a second order in time, so we need two layers in time. So we also need to specify two.
Sorry, Thomas, can I ask, I mean, so this time, can it be exponentially large in the...
No, it's actually n squared. It's a little bit of combinatorics to show that it's bounded by n squared. Actually, it's less. It's 3, actually. I mean, n squared is a trivial bound, but it's much better than that. It's less than 3 over 2 times n plus a constant. So it's a linear in n, which is sort of more or less expected based on what we know from Ljubljana dynamics, quantum Markov chains with boundary driving. There is a more or less seems to be similar for this, but it's okay. That's sort of. I mean, here it's easy. Let's say at least. Okay, so now let me go to the steady state. How does the steady state look like? The steady state basically is a fixed point of u, but a fixed point of u is a kind of a joint fixed point of intertwined fixed points of ue and uo. So it's a pair of probability state vectors which are intertwined by ue and uo. This just comes from the fact that you have a second order differential equation if you want it to start with. So you have two layers that determine the next layer in time. I mean, this is just the way you want to write it, to have equations which determine that the solution is simpler. Okay, so how does it look? I mean, this is a state which I sort of decided to, we decided to call it a patch state. I don't know why, it's somehow found this word suitable for that. It's a kind of a matrix product state, but it's not, it's much simpler than matrix product state. Basically, it's a commutative matrix product state. It's a diagonal matrix product state if you want. I mean, basically you can just ask how would this be rephrased in terms of quantum states. I mean, basically our steady state is a purely diagonal density matrix. Yeah? So, basically you have to write an MPO for a diagonal density matrix. And it turns out this is basically what it is here. Yeah. So, So this is the statement. Yeah. So the statement is that for an open set of driving parameters. So there could be complications when one of these driving parameters would be exactly 0 or 1. Then I would have, I mean, even with the previous theorem, there could have been problems. But so suppose that all the rates, all the probabilities are strictly between 0 and 1. Then the statement is that both probability state vectors at two subsequent layers of time for the steady state can be written in terms of, there is all the components, all to the 2 to the n components, can be written in terms of a product of this rank 3 and rank 4 tensors, such that the two subsequent coefficients, the states of two subsequent cells, enter as indices on these tensors and overlap. So there is S1, S2, S3, S2, S3, S4, S5, S5, S4, S5, S6, and 7, and so on and so forth. So diagrammatically, this is like this. Now again, there should be light gray boxes around this, but anyway, it's clear enough, I guess, as it is shown here. So this is like the number of cells. So this is like these tensors, and now, I mean, it's more or less, one has to compare this to these tensor networks that has been discussed this morning, but there is no, when you contract some, I mean, there is no contraction here, because everything is diagonal. So you don't sum over indices. All the indices are fixed, and you don't sum over them. So it's really embarrassingly simple, right? I mean, it's, so if anyone knows anything related, I'll be happy to learn. I mean, it's really, I mean, that should have been discussed already, in classical, well, I mean, I don't know. It's, why people would bother about this, right? So it is very different, for example, than in stochastic classical dynamics, where you have these non-commutative concepts like matrix product states, right?
Yeah, but they can also be one-dimensional representations in that case, which would be
right. But this is not what I mean one-dimensional representations.
no, basically, it's not a matrix; it's a scalar.
Right, but this is not one-dimensional in the sense that this is strongly correlated state.
Okay.
This is not a product state. This
Yeah,
state
no,
is strongly correlated, but it's commutative, or it's diagonal if you want. Right. So it's a kind of parametrization. I mean, one can also build sort of a classical DMRG on top of that if you want. I mean, this could be like a variational state on which you want to optimize your steady state, a fixed point, or some other Markov chains if you want. Okay, so yeah, so now let's try to, first this is a Gansatz. Now let's try to guess or to find some sort of sufficient set of equations from which we will determine these tensors left, right, and x, and left prime, right prime, and x prime. So actually this is like 8 plus 8 plus 8 plus 8 plus 16 plus 16, that is in total 64 numbers, right? So it shouldn't be too difficult to get 64 numbers, right? Okay. So now I will just sketch basically the idea of the proof. I mean, the proof maybe is not so elegant at this point. It's a kind of a brute force approach, but at the end maybe I will try to make some sort of more appealing interpretation of the solution of this process. So first of all, idea is find a minimal set of equations to determine these so-called patch tensors. And then we will verify that these patch tensors satisfy, for example, Markov fixed point condition for a fixed, small, let's say, but even number of sides. For example, n equal to 8 seems to be somehow sufficient. And then we will show that there is an inductive stack. Once we have shown that we have solution for a finite n, then we can basically build up a sufficient set of equations from which we can show that we have also solution for n plus 2. So that's again very elementary. So let's first write down the minimal set of equations. So now we have to just, what we have to do now is we have to plug this ansatz into the defining equations for some specific combinations of S1, S2 to S8, for example, or even less. And we decide to do that for a trivial, let's say for some, I would call this cluster configurations. For configurations which are almost all the time vacuum, and then there is some burst of activity somewhere, and then there is a vacuum again. So for example, when there is a burst of activity on four adjacent sides, S prime, U prime, for example. And then you connect the left and right hand side of the equation, you get some equations, some nonlinear equations for the x prime, x, L prime, L, R prime, R, right? So these are the equations. You see that the only thing which enters these equations is this mapping chi, which is this 54 rule, and these matrices PL and PR, which are these 4x4 matrices which specify the boundary. Okay, as much horrible as these equations look, I mean, of course, then again, one relies on Wolfram's Mathematica for that. I mean, this is not something you want to do by hand. But then, okay, then you play with it, and then you find that there is an ansatz which only involves 22 parameters. You know, having these 64 numbers depending on 22 parameters. There are some symmetries, actually, which I will not discuss here. There is some sort of a gauge symmetry. Obviously, there is a gauge symmetry, right? So you can always multiply here by g minus 1, g minus 1 to somehow choose a particular set of x's to be 1. You exercise the symmetry, but still you have 22 parameters, and then you get some set of equations which is enough to solve this by this Grobner basis algorithm, right? So there is a unique solution for that, and I will only write the components of the solution which concern the bulk tensors. So there is the boundary tensors, which for the moment I will not care about. Let's just write down okay, there are 22 parameters, but the first 5 parameters determine the bulk tensor. So you see these are the bulk tensors, the first 2 columns, and they only depend on x1, x2, x3, x4, and x5. And these are now given in terms of, you see, very nice algebraic functions, rational functions of lambda and u, and lambda and u are just the differences of the chemical parameters of the left and the right Markov chain. So lambda is alpha minus beta, and u is gamma minus delta. So these are a kind of voltages, if you want, or chemical potential drops or whatever. So this drives the currents. Yeah? So now let's see if we can compute observers from there. Okay, now we should still provide, I mean, this is now the solution. Now we should still provide the rest of the proof that this solution solves the problem for any component of the probability state vector. So any equation of the fixed point. Fixed point is a matrix equation, so for any component of this matrix equation, and also for any system size. And actually this induction is equivalent to demonstrating this strange-looking set of I would somehow, I mean, I would call them some sort of fusion conditions, right? So now you need to go from product of 2 x's to product of 3 x's in order to be able to go from n to n plus 2. And there is a sufficient condition for that, which is this horrible identity. But this identity is not so horrible. I mean, actually, this identity has 2024 components, but they are all kind of trivially satisfied for this solution that we have just found. So. Okay, yeah, now I would like to see whether there is some Young-Baxter equation here, right? I mean, this is integrability, by the way. So there should be Young-Baxter equation or star triangle equations popping up somewhere. So, but they are still not here. I mean,
a little bit like some RSOS formality, no?
Pardon me?
The object X looks like objects you use in a RSOS description of.
In what? In
RSOS models.
RSOS, yeah. Well, we can discuss. I don't know. But anyway, I will show you. I mean, later now I will try to come to some sort of Lux pair, some sort of zero curvature condition which is equivalent to this. But okay, yeah. So, but let's first ask the question: how we compute observers now? I mean, basically we have solved the problem. Now, how to compute observers? First, let's normalize the probability state vector, right? So the first object that you need to control is the so-called non-equilibrium partition function, which is just the sum of all probabilities of your non-equilibrium steady state. And by the way, now this can be written in terms of product of matrices. So when you sum over all components of the S, now remember how this ansatz looked like. Now this amounts to multiplying the matrices. When I take a multiple sum here over S1, S2, S3, S4, S5, now this is then like treating this X as a 4x4 matrix, considering first 2 indices as row and last 2 indices as column. And this is like just doing this. So this is what actually we are doing here. Okay, here. So basically, this can be written now as a vector, a 4 vector times a 4 matrix to the power n over 2 minus 2, because there is n over 2 such matrices roughly. And there is probability. Both vectors have to be both vectors z, p and p prime have to be normalized. So these two partition functions at 2 subsequent layers have to be identically equal, right? And okay, here this is the definition of the boundary vectors. So there are boundary vectors little l, little r, little l prime, little r prime, which is just the redefinition of the rank 3 tensors. And transfer matrices. Now I'll define the object which I would like to call a transfer matrix, which is just a redefinition of the tensor X. Yeah. And now, since the since the two partition functions have to match, since my dynamics conserves probability, one should have this isospectrality condition, namely T prime should be similar to T. So there should be an intertwiner W which somehow maps T to T prime. And this is my lax sort of picture of this integrable process. Yeah? So let me try to be more, let's say, more clear on this. I mean, this is kind of probably the most interesting, at least mathematically interesting part of this discussion, even though maybe it's sort of strange. But still, I mean, let me now try to define something which I would like to call as spectral parameters. So now, where are the, I mean, now basically everything depends now essentially on two parameters. There are four parameters, but the bulk tensors depend only on the differences, and the boundary vectors basically depend on the other two, but it's not crucial. So, but let's discuss now just the boundary transfer matrix. So let me now just define the spectral parameters as two combinations of lambda and mu. Lambda and mu I would prefer to call driving parameters because they are coming from physics, from the chemical potentials of the boundaries. Now, if I define x4 and x5, basically these are a function of lambda and mu, and if x4 is phi of lambda and mu, then x5 is just phi of mu and lambda. So it's just a permutation. So I will define these two numbers, which are sort of independent, for an independent set of lambda and mu. I will define these two numbers as omega and psi, and I will call them spectral parameters. And this function phi is this function here. Now, why should I do this? Because now these transfer matrices look fantastically simple. They look simply like this, right? So all the elements of these transfer matrices are simple monomials of order 1 or minus 1 of this psi and mu. I mean, after all, this has to be simple because bulk dynamics is a permutation. So to characterize this permutation by some algebra, this has to be simple, right? So now, how should I now define this intertwiner? I mean, how this intertwining should now be defined? So now, okay, there is also this W. There is this intertwining which I wrote here. So T prime is similar to T, and then there is this similarity intertwining transformation W, and this W again is a simple matrix. Is this one? And moreover, I mean, if I write this T prime as a function of psi and mu, you see that this is the same function as T with psi and mu reversed, which is after all not so strange if you imagine what this actually means. So this is basically my sort of favorite Lax pair formulation of this process. So this is the inversion identity, and this is the commutativity, if you want. Okay, so now let me just compute some density profiles. So how does this dynamics look? Obviously, it's ballistic. I mean, they are solitons, so you wouldn't expect that there would be some drop of potential, right? Drop of density. So let me just calculate this density profile, and at the end of the day, what we get is that density is constant in the bulk, and then there are drops near the boundaries. That's something very common for integrable system. I mean, for ballistic integrable system, you will have flat density, and then there will be some drops near the boundaries. Okay, for example, you can also calculate any k-point correlation function, again, using the same sort of transfer matrix. For example, density correlation has exponential decay, and there is a decay length associated to that, which is related to the ratio between the leading and subleading eigenvalue of this transfer matrix. Again, this can be written as an analytic function of the system parameters, and this is just an example for that. So you see, okay, I have exponential decay of correlations, but nevertheless. Anyway, and then you have, for example, you can compute a steady state current. You have a steady state current of solitons. Actually, by the way, this is a conserved charge for the dynamics. And I will come to conserved charge in 2 minutes. But let me just stress, this is not only that this is a current, the steady state current, which is obviously well defined for a steady state, but this is also exactly conserved charge and satisfies a local conservation law for the bulk dynamics.
What happens when the denominator is 0?
When the denominator is 0, the denominator cannot be 0 when I'm in my compact set of parameters where I exclude 0 and 1. This is another reason why I should exclude 0 and 1. You see, I mean, if you look, there is this 8. This 8 prevents you, and lambda and mu are all between -1 and 1, not including the endpoints. So you will always be away from singularity. But yeah. By the way, it's also interesting to stress that these densities are limited. Not, I mean, I can by this Markov process, I can not reach densities arbitrary densities. My densities are limited from 0.4 to 2/3, so from 2/5 to 2/3. So actually, I cannot cover all the densities, yeah? So I'm kind of limited. But still, I mean, there's a macroscopic set of densities which I can reach, and so yeah, I can go far from, let's say, far from equilibrium if you want, but still. Okay, so yeah, so now let me go to the last thing which I can seriously discuss in this talk, and this is the complete set of local conserved charges. So now the question is, do we have local charges here? I mean, do we have quasi-local charges, for example? I believe we do, but we are not quite there yet. But let me just show you how we classify the complete set of conserved charges based on the transfer matrix I have just presented. Okay, so so now I'm just following what I have learned about quantum spin chains, just transcribing it for the classical reversible cellular automaton. So I would like to consider this as an observable now. I mean, this is basically a fixed point. I mean, I would like to have, well, I mean, this is kind of obvious, but it requires a little bit of thinking to appreciate that. But if you take periodic boundary conditions, then the product of these x's now but at the end not putting left and right tensors, but just wrapping it around and making it periodic, then obviously I get an observable which is preserved by this permutation periodic PBC. So UPBC is now just a product of permutation, so it's a pure permutation. So I have a very boring many-body permutation, and I have a two-parameter family of 2 to the n component vectors which are preserved by this permutation. So now, and this is basically has been derived in previous slides. Yeah? So now I try to learn whether I can compute some conserved charges of these, if you want, of this permutation dynamics based on this let's say. Yeah, this would be, this is something which would be analogous to transfer matrix of a spin chain, of a Heisenberg spin chain, if you want. Now, it depends now on two spectral parameters, but this is something which commutes with the Hamiltonian. In this case, it's preserved by dynamics. And now you would like to make some sort of a logarithmic derivative of that to arrive at the local sum of local densities which are satisfying local continuity equation. And this is the program I want to show here, just in 1.5 slides. So I just remind you on the structure of the transfer matrix. And basically, but now you see, I mean, the fact that transfer matrix is so embarrassingly simple that it has only monomials of psi and omega means that if I take the product of these matrix elements, any product of these matrix elements, then I take the logarithm. I mean, this is, you can think of this as basically really as a quantum spin chain which is purely commutative. So my, so basically what I do now is the same as people do in quantum spin chains, but now the logarithm of the transfer matrix now is just the logarithm of its components because everything commutes. So you can basically work in component-wise. Yeah. So the point is now that the matrix elements, diagonal matrix elements of the transfer matrix are just products of monomials. And once I do the logarithm of monomial, I get a linear combination of the log of the variables, right? So there are only two okay, so here I missed it. Okay, so I should have derived here with respect to the log of but never mind. With respect to the log of psi and omega. But never mind. I mean, there are just linear functions of log psi and log omega, and so there are just first derivatives which are non-vanishing, and all the other derivatives are trivially zero. So sorry for that. I mean, I should have defined here variables which are log omega and log psi. And all other derivatives are strictly zero. So there are only two charges which can be written in terms of translation invariant sums of some densities, which depend on states of 4 adjacent sites. So both charges are of, well, I mean, formally there are order 4, but the first charge actually involves, so these are the two densities, Q1 and Q2. The first charge involves only 3 indices, S, S prime, and T, and this is exactly the soliton current. This is the density of right movers, and this is the density of left movers. So that's the difference of the two, which is the net soliton current. But the other charge is kind of more interesting. It's a kind of effective Hamiltonian, if you want. It is it's a Hamilton. This is like a current type charge, and this is more like a density type charge. I mean, it's left-right symmetric. Anyway, okay, so that's basically all the technical parts of this talk. Now, what to do next? Okay, I mean, I'm not sure if you are amused by this, but I was very much amused, even though I have not found, I mean, apart from technique, of course, I have not found any physics here, but since we are interested in techniques, the question is, can we do more? And we are all interested, for example, to find some exact results about decay modes of quantum Markov chains, right? About, let's say, Ljubljana dynamics, Ljubljana dynamics. And in this case, for example, I think we have not there yet, but I think it should be possible to find exact results also on the full spectrum of this Markov matrix. This is just numerics so far, but this numerics is very suggestive. I mean, this is full spectrum of the Markov chain for a chain of size 8, 10, and 12. And you see there are these daisy structures, and each leaf of this daisy basically is like a band, and there are two extreme states. So these are all eigenstates of Markov chain. But these colored points are extreme states, and the colors means the Schmidt rank. So I do the bipartition here, and I compute the Schmidt rank. The red means Schmidt rank 3. Basically, it's this, you know, it's not 4, but it's 3. But I didn't bother to explain why I have sort of slightly smaller Schmidt rank that I could have. But matrix X is 4 by 4, but only it has three non-zero eigenvalues, so that the steady state has Schmidt rank 3. With respect to every cut you like, and then there are other eigenstates which have Schmidt rank 3, which are all the red points, and then there are these blue points, and the blue points have Schmidt rank 6, and this Schmidt rank is independent of the system size. So which means that there should be again a patch state ansatz or a matrix product ansatz or whatever. There should be a way to write this analytically. So that is sort of the next sort of, if you find enough.
What happened to the gap when n?
To a gap? Yeah, that's a good question. I don't know what happens to the gap. Gap shrinks slightly. I mean, I guess it goes like 1 over n, I would say. Well, actually, it goes. I mean, this theorem 1. I mean, this estimate on the, you know, on the number of steps in Markov graph required to reach arbitrary point from any other point suggests that the gap closes as 1 over n. And this is what this seems to be what's clear from this picture. Yeah, this is 8, 10, and 12. It closes as 1 over n. And it's also intuitive, all right? I mean, it takes like, it's ballistic system, so it takes like n steps to go from anywhere to any other place. So. Okay, so that's basically, I have not prepared any conclusion slides, so that's basically all I want to say about this model. Now the question is what to do next, of course. I mean, this is, if you want, this is a very artificial model. But now we can immediately imagine that we can do much more physical models from here. For example, the model which I would really like to see would be a continuous model. I mean, model which is defined still on the discrete lattice, but for which the variable is continuous. I mean, here variable was Z2, so it's really artificial. But now let's take, for example, nonlinear Schrödinger lattice, nonlinear Schrödinger equation on a lattice, right? This Ablovitz-Ladik system or whatever, which is defined on a discrete lattice, but the variable there could be a continuous variable. So can we just rerun this program for that? I think we can. I mean, what we now have to do, I think that the principal equation which we now have to understand is this fusion relation equation which I stressed here. I mean, now this equation suddenly becomes some set of functional equations for four variables, because now these V, S, S prime, and so are now continuous variables, or let's say phases or whatever, or amplitudes of your of your field. And then what you have to do is to find some non-trivial solutions, and I am betting these non-trivial solutions will provide steady states of this more interesting driven classical integrable systems. Okay, and yeah, by this I would like to conclude, and thank you for your attention.
Some questions?
Like speaking of making them more physical, is there a way of making the rules asynchronous, or then throwing the time continuous limit to make it Ljubljana dynamics?
Yeah, that's also
would be like a nice
that's also interesting. Yeah.
But that would be like the limit of a driven quantum chain with two reservoirs or so.
Yeah, but okay, no, but yeah, that also would be interesting. Yeah. Anyway, you would have to make time continuous to go to any interesting, let's say, physically interesting model. So,
but once you're asynchronous, the time continuous limit is pretty much for free, right?
Yeah.
Because then
Yeah.
it's clear how to make that transcription.
Yeah, but you can basically, maybe you can also make it with a synchronous process.
Right.
Yeah, but I think if you want to go, for example, to nonlinear Schrödinger, you have to do it also. You have to also do the other limit, as you say. I mean, the continuous time limits. Yeah. No, I mean, I think it's worth to try. I mean, we have not done yet. This is just fresh result, but.
Can you compute some large deviation function first?
To put what?
Compute some large deviation function.
Large deviation. Yeah. I think again. I mean, we have not tried yet. I mean, this is. Yeah, I asked Carlos to do it, but because he's more expert on that than me. But
Are there Z1 versions of this model?
pardon me.
Z1 version.
ZN, yeah. Well, that's another thing. I mean, not particularly of this model, but then there is this, as I say, second part of this remarkable paper by Bobenko et al., where they discuss this Lux formulation for Hirota equation on finite fields. And that I would see, for example, that would be probably the next model to try. Yeah, because that I guess should be going quite straightforward. But we have not yet tried.
Some more questions?
Have you looked at possible background transformations since you have soliton content?
Possible what?
Background transformation.
Background transformation. No.
Because your rational expressions that you call fusion relation, that's what they look like.
Ah, okay. So no, I haven't thought about this. No.
The root transformations would be generalized.
No, I have not thought about this.
The
No.
Bobenko paper is quite old, and I think there has been a lot of progress also in understanding the ultra-discrete limit of classical integral systems, which basically produce cellular automata. So it might be good to check with the classical integral systems community if this is a limit of a ultra-discrete limit of a known classical integral system.
You mean this equation? Yeah, that's very interesting.
So in these ultra-discrete limits, it's basically related to tropical geometry. You come out at cellular automata from what used to be a fully fledged nonlinear PDE.
Mm-hmm. Yeah, thank you. I mean, maybe we can talk more about this.
There's some more questions. If not, the stage is speaking again.